In mathematics, more specifically in abstract algebra and linear algebra, a bilinear form on a vector space V is a bilinear map V times Vk, where k is the field of scalars. In other words, a bilinear form is a function b, V times Vk which is linear in each argument separately. B equals B plus B, B equals B plus B, B equals B equals lambda B. The definition of a bilinear form can be extended to include modules over a commutative ring, with linear maps replaced by module homomorphisms. When K is the field of complex numbers C, one is often more interested in sesquilinear forms, which are similar to bilinear forms but are conjugate linear in one argument. Coordinate representation. Let V naughts be an n-dimensional vector space with basis E1, n. Define the n times n matrix A by Aij equals B. If the n times 1 matrix X represents a vector V with respect to this basis, and analogously, Y represents W, then, suppose F1, Fn is another basis for V, such that F1, Fn equals E1, n S where SGL. Now the new matrix representation for the bilinear form is given by stars maps to the dual space. Every bilinear form B on V defines a pair of linear maps from V to its dual space V. Define B1, B2. VV by B1 equals B, B2 equals B. This is often denoted as B1 equals B, B2 equals B, where the dot indicates the slot into which the argument for the resulting linear functional is to be placed. For all implies that x equals 0 and for all implies that y equals 0. The corresponding notion for a module over a commutative ring is that a bilinear form is unimodular if V is an isomorphism. Given a finite-dimensional module over a commutative ring, the pairing may be injective but not unimodular. For example, over the integers, the pairing B equals 2xy is non-degenerate but not unimodular, as the induced map from V equals Z to V equals Z is multiplication by 2. If V is finite-dimensional, then one can identify V with its double dual V. One can then show that B2 is the transpose of the linear map B1. Given B1 can define the transpose of B to be the bilinear form given by TB equals B. The left radical and right radical of the form B are the kernels of B1 and B2 respectively. They are the vectors orthogonal to the whole space on the left and on the right. If B is finite-dimensional, then the rank of B1 is equal to the rank of B2. If this number is equal to dim, then B1 and B2 are linear isomorphisms from V to V. In this case, B is non-degenerate. By the rank nullity theorem, this is equivalent to the condition that the left and equivalently right radicals be trivial. For finite-dimensional spaces, this is often taken as the definition of non-degeneracy. Definition: B is non-degenerate if B equals 0 for all W implies V equals 0. Given any linear map A, VV1 can obtain a bilinear form B on V via B equals A. This form will be non-degenerate if and only if A is an isomorphism. If B is finite-dimensional, then, relative to some basis for V, a bilinear form is degenerate if and only if the determinant of the associated matrix is 0. Likewise, a non-degenerate form is one for which the determinant of the associated matrix is non-zero. These statements are independent of the chosen basis. For a module over a commutative ring, a unimodular form is one for which the determinant of the associate matrix is a unit. Hence the term. Note that a form whose matrix is non-zero but not a unit will be non-degenerate but not unimodular. For example, B equals 2xy over the integers. Symmetric, skew-symmetric and alternating forms. We define a form to be symmetric if B equals B for all V, W in V. Alternating if B equals 0 for all V in V. Skew-symmetric if B equals minus B for all V, W in V. Proposition: every alternating form is skew-symmetric. Proof: This can be seen by expanding B. If the characteristic of K is not 2, then the converse is also true. Every skew-symmetric form is alternating. If, however, char equals 2, then a skew-symmetric form is the same as a symmetric form, and there exist symmetric, skew-symmetric forms that are not alternating. A bilinear form is symmetric if and only if its coordinate matrix is symmetric. A bilinear form is alternating if and only if its coordinate matrix is skew-symmetric and the diagonal entries are all 0, 2. A bilinear form is symmetric if and only if the maps B1, B2, VV are equal, and skew-symmetric if and only if they are negatives of one another. If char 2, then one can decompose a bilinear form into a symmetric and a skew-symmetric part as follows, where TB is the transpose of B. Derived quadratic form. For any bilinear form B, V times VK, there exists an associated quadratic form Q, VK defined by Q, VK, VB. When char 2, the quadratic form Q is determined by the symmetric part of the bilinear form B and is independent of the antisymmetric part. In this case there is a 1-to-1 correspondence between the symmetric part of the bilinear form and the quadratic form, and it makes sense to speak of the symmetric bilinear form associated with a quadratic form. When char equals 2 and dim v greater than 1, this correspondence between quadratic forms and symmetric bilinear forms breaks down. Reflexivity and orthogonality. Definition. A bilinear form B, V times Vk is called reflexive if B equals 0 implies B equals 0 for all V, W in V. Definition. Let B, V times Vk be a reflexive bilinear form. V, W and V are orthogonal with respect to B if B equals 0. A form B is reflexive if and only if it is either symmetric or alternating. In the absence of reflexivity, we have to distinguish left and right orthogonality. In a reflexive space, the left and right radicals agree and are termed the kernel or the radical of the bilinear form. The subspace of all vectors orthogonal with every other vector. If vector V, with matrix representation X, is in the radical of a bilinear form with matrix representation A, if and only if X equals 0 XTA equals 0. The radical is always a subspace V. It is trivial if and only if the matrix A is non-singular, and thus if and only if the bilinear form is non-degenerate. Suppose W is a subspace. Define the orthogonal complement for a non-degenerate form on a finite-dimensional space. The map WW is bijective, and the dimension of W is dim minus dim. Different spaces. Much of the theory is available for a bilinear mapping to the base field B, V times WK. In this situation we still have induced linear mappings from V to W, and from W to V. It may happen that these mappings are isomorphisms, assuming finite dimensions. If one is an isomorphism, the other must be. When this occurs, B is said to be a perfect pairing. In finite dimensions, this is equivalent to the pairing being non-degenerate. For modules, just as how a non-degenerate form is weaker than a unimodular form, a non-degenerate pairing is a weaker notion than a perfect pairing. A pairing can be non-degenerate without being a perfect pairing. For instance, Z times ZZ via 2xy is non-degenerate, but induces multiplication by 2 on the map ZZ. Terminology varies in coverage of bilinear forms. For example, Rees-Harvey discusses 8 types of inner product. To define them he uses diagonal matrices Aij having only +1 or -1 for non-zero elements. Some of the inner products are symplectic forms and some are sesquilinear forms or Hermitian forms. Rather than a general field K, the instances with real numbers R, complex numbers C, and quaternions H are spelled out. The bilinear form is called the real symmetric case and labeled R, where P plus Q equals N. Then he articulates the connection to traditional terminology. Some of the real symmetric cases are very important. The positive definite case R is called Euclidean space, while the case of a single minus R is called Lorentzian space. If n equals 4, then Lorentzian space is also called Minkowski space or Minkowski spacetime. The special case R will be referred to as the split case. Relation to tensor products. By the universal property of the tensor product, bilinear forms on V are in one-to-one correspondence with linear maps VVK. If B is a bilinear form on V, the corresponding linear map is given by VWB. The set of all linear maps VVK is the dual space of VV. So bilinear forms may be thought of as elements of VV. Likewise, symmetric bilinear forms may be thought of as elements of Sim2, and alternating bilinear forms as elements of lambda2V, on normed vector spaces. Definition. A bilinear form on a normed vector space is bounded, if there is a constancy such that for all u, VV. Definition.